winter school on quantum revolutions in AMO science, I thought it needs a lecture about entanglement in many-body systems. Yeah, so before I dive into the details, I have one slide about revolutions in AMO science, or at least where these revolutions led us today. So I made a slide about recent advancements in AMO science, and it's really amazing. A lot of these things that you can see here on this slide, I personally revolutions in AMO science, but none of the things that you see here is actually older than 2 years. So in this winter school, you will hear a lot about Rydberg atoms and optical tweezers. You might have heard already something about these things from Harry yesterday, maybe. And on Thursday, Misha will give you 3 lectures where you learn about these things in all great detail. These things are extremely flexible. You can build tweezer arrays in 2 and even 3 dimensions and arrange these things arbitrarily. And we have seen many examples where these things realize correlated phases of matter. Another platform that's maybe a bit underrepresented here at this winter school are atoms in optical lattices. And there, something that what I always like to emphasize is that we have a feature in AMO physics, which is that we have fermions. If you think about it, there is actually no other platform out there where you have fermions naturally available. And in atomic physics, we have atoms that are naturally fermions, and we should kind of use what nature gives us. And there has been a recent breakthrough actually in the systems, which is that now recently, this is an archive paper from a week ago, it is now possible to cool the systems in a regime where actually numerical methods start to have a lot of problems, and it might be very interesting, to study now, is there like high temperature superconductivity and other things. Ions is another interesting platform. I think they are also a bit underrepresented at this winter school. Also here in the last 2 years, we have seen now a lot of progress. These ions are now shuttled around these days and have been used to realize topological phases of matter. And now, since a year and a half or so, it became possible to arrange these ions in static 2-dimensional traps. It's also a new development. And the platform that's currently starting off is molecules. So very recently, molecules can be trapped into tweezers, and laser cooling techniques have been developed for molecules. So all of these enormous breakthroughs kind of, they happened during the last 2 years. And you can sort of ask, why are these systems interesting? Why do we care? And the reason is entanglement. Like if there would not be quantum entanglement in the systems, nobody would care. This is really what makes the systems unique, what makes the systems different from classical systems. And this is what this lecture is about. So since we have now 2025, we are celebrating sort of 100 years of quantum mechanics. In 1925, Heisenberg discovered quantum mechanics. It makes sense to look a little bit at the history. Entanglement, at least the word, was introduced in 1935 by Erwin Schrödinger. And Erwin Schrödinger wrote a paper in 1935 where he described it as what it means for him is that maximum knowledge of a total system does not necessarily include knowledge of all of its parts. And what this means for a many-body system is that if we have some many-body system in a pure state psi, and we cut out the subsystem A, and we ask about the entanglement, like how entangled is the subsystem A with its environment B. What it means, actually, if you just look at subsystem A, you don't learn much about the system. Yeah, so the information is actually, the information contained in the state is actually in correlations between A and B. And this is actually, as you will see later, also the way how we quantify entanglement, how we measure it. It's all of that we look at the subsystem and we look at the information that's missing from the subsystem. And this can be quantified in terms of an entropy. So entanglement is historically very important, like for the philosophical foundations of quantum physics. As many of you might know, Einstein didn't like it at all. But this lecture is more about why do we care today about entanglement? Why do we care in many body physics? And there are a couple of reasons. Actually, entanglement is sort of the base, is at the very basis of quantum complexity. Entanglement is actually the reason why we cannot simulate these complicated many-body systems classically. So highly correlated states are hard to simulate. Some people here that are working in digital quantum computing might disagree with me. There are some exceptions, which is if you write down quantum circuits which don't have magic. Does anybody know? Does everybody know here what magic is? Okay. So if you sort of build circuits that are just composed of these gates, of C0 gates, Hadamard's, S gates, and Pauli gates, you can these circuits they generate a lot of entanglement, but you can simulate them classically. But apart from this exception, like if the circuits contain magic, then actually there is no dispute that it is actually entanglement, which makes them hard to simulate classically. Another thing is also if we have tools for measuring entanglement in these many-body systems, then we can sort of verify quantum simulation and quantum computing experiments, right? You want to see that your experiment is not doing something classical. You want to sort of see entanglement. It is important for studying fundamental physics, like the area laws or volume laws of entanglement. I will comment on these things towards the end of the talk, and you can use it to study quantum phase transitions. You can use it to characterize topological phases of matter. I will also talk about this later. You will see how this works. I will make comments on that. You will also learn quite a lot about error correction at this winter school. And it turns out that entanglement is also at the basis of quantum error correction. The very idea of quantum error correction is that you encode information redundantly in many qubits, such that if you look, for instance, at a single qubit or at a small subset of qubits, they contain no information. So if the environment comes along and tries to measure these qubits, the environment doesn't learn anything about the encoded information, and in this way, the information is protected. So for all of these reasons, we are sort of interested in studying quantum entanglement. All right. So about this talk, I would sort of start with the absolute basics. So the experts on entanglement might be a little bit bored about these things. I would say a lot of things that many of you guys will already know, but maybe you know it comes with in a bit of a different flavor. Then I will talk about how we measure entanglement in modern experiments. I will talk about two-copy interference, and I will make some comments here about modern developments like random measurements, Bell sampling, and virtual cooling. And towards the very end, I hope I will have time for that. I will talk about more modern ways about looking at entanglement Hamiltonians, and then I will make some comments about entanglement spectroscopy. If there are any questions, please interrupt me anytime. Okay, it's very, very informal. All right. So I will start by entertaining you a bit with a little bit a different way of thinking about qubits. So all of you know, actually this is something that all of my three lectures will have in common. I will always talk about qubits, even though many of the things I say will apply to other systems as well, like to large spins, to bosons, to fermions. But for a qubit, all of you know that the way we describe a single qubit is with this vector on the Bloch sphere. And there is a little bit a different way of thinking about these qubits, and this is inspired by John Preskill. For the next 10 minutes, I sort of will draw from some of his lectures. I adopted them a little bit. So a different way of thinking about these qubits is to think about them as a box. As a box with three doors. We call them door number 1, door number 2, and door number 3. And you can open these doors, and when you open them, a ball comes out, either a red or a blue ball. So you can open door number 1, a blue ball comes out. And what this means on the Bloch sphere, opening door number 1 for me is a measurement along the C basis. So we found the state 0. Yeah, you can also then open door number 3. This is a measurement around the y basis, and the state minus y comes out. It's a red ball, or door number 2. You know, you can open this box in different ways and measure these qubits. And this is also a complete representation about the qubit. Like if you repeatedly prepare this qubit and you open all of these 3 doors, you can actually learn where this vector points on the block sphere. It's that the whole information is contained. This, you know, repeatedly opening these doors is called quantum state tomography. All right, so single qubits are really not very interesting. It becomes interesting if you entangle them. So we now look at an entangled qubits. So we prepare 2 of these qubits at an entangled state. And an entangled state has the following feature. What I do now in this animation, I repeatedly prepare pairs of these qubits, and we just look at one of these qubits now at the length one. And in these entangled states, the following thing happens. If you repeatedly open the doors, you always get a random outcome. Always 50% blue, 50% red. No matter which door you open, if you door number 1, 2, or 3, it's always completely random. Now let's do the same and just look at the right qubit. I open 3 times door number 1, sometimes red, sometimes blue. I open 3 times door number 2, sometimes red, sometimes blue. It's no matter what you do, it's completely random. And this means that neither one of these qubits contains any information, right? So you open the doors, it's completely, you don't learn anything about this qubit. But the thing about entanglement is, if you open the same door on both of them, you see the same thing in this particular state that I'm describing here. So if you open the same door on both of them, the same ball comes out. It's completely random on both of them individually, but if you do the same, you see the same. So the information is really encoded in correlations among the qubits and not in the qubits themselves. This is what Schrödinger meant by complete knowledge of the total system does not reveal any knowledge of its parts. Okay, but this, I explained this once to a friend of mine, and he immediately got the point that this is actually not interesting at all. It's completely, it's not interesting, because this can be produced classically, completely classically, right? In the following way, we prepare these boxes, it's already predetermined which ball comes out from these doors. So we have these 2 boxes, they are prepared in a certain way, the balls are already waiting behind the doors. And now if you open door number 1 on this one, a red ball comes out, and if you do it here, a red ball comes out just because they are the same. Or if you open door number 3, a blue ball comes out, and here just the same thing happens because these boxes are just equivalent. And for some reason, if you open a door, the other 2 balls disappear. And the interesting thing about entanglement is actually that it's not like this. You know, it's not that. And why do we know? From where can we tell? We can tell by opening different doors on the boxes. You know, if you open door number 1 here and door number 2 here, you can see that it is not like this, that the balls are waiting behind the doors. And how do we see that? Let's think a little bit about this. What can we actually tell about these boxes if we open different doors on them? So if you have 2 boxes, there are 6 different ways of opening different doors on them, right? I have 3 options for one box, and then I should open a different door, so I have 2 options for the other. 3 times 2 is 6. And these are the 3 options. Now we know that these boxes are equivalent, they are completely the same, right? So I can exchange them. So actually there are just 3 options for opening different doors on these boxes because they are the same. And what kind of outcomes are possible? We have 3 different ways of opening the box to door number 1, 2, or 3, and 2 colors. So 2 to the 3 is 8. This box can be prepared in 8 different ways. These are these 8 ways here. And what do we see if we look at these boxes? Turns out that there are always in all of these 8 options, 2 of the balls have to be the same, right? Completely completely obvious. We have three balls and two colors. There is no way that all three of them can be different. Two of them have to be the same. So this means that if we open these doors randomly, like one of these three options have to reveal balls of the same color. So we have a conclusion: if we open different doors on these boxes, in at least 1/3 of the cases, we must see the same color. Right? There is no other way. So it must be. Now, experiments can be done with these two boxes. You open different doors, and there are entangled states where the following happens. We see the same color in only a quarter of the cases. So this is classically completely impossible. Well, I explained this to a friend of mine, and he said, okay, so what can we make fun with this? So we were sitting together at an evening, and discussing a bit, and actually came up with a stupid unquote thing. Let's imagine the following: that Alice and Bob go to a casino, and the game is the following: the croupier distributes two boxes to Alice and Bob, and the cube guarantees that these boxes are the same. They are absolutely equivalent, which Alice and Bob can verify anytime they want. They open the same door and they see the same ball. But the rules of the game now is that they have to open different doors on the boxes. So they are not allowed to open the same door if they want to win something. So they have to open different doors. And if they see the same ball, they win. And the croupier plays them $8. And if they open different doors and they see different colors, they lose and they have to pay $3 to the croupier. So the question is, should they play this game? And the answer is, if these boxes are classical, then you will see for sure the same color in 1 out of 3 games on average. So 2 times you have to pay $3, this is $6, and you win $8 here, so you win $2 per 3 games on average. But if these are quantum boxes in this particular state, then you see the same color only 1 out of 4 times, and you can do the math yourself. They lose $1 per 4 games. So that's a kind of a stupid casino because it's a casino based on the fact that the players don't know quantum mechanics. So if you would be my players in this casino, I would not gain any advantage. But okay, the interesting thing about it is that this is a quantum thing, right? So you can think about, is it somehow possible to program these boxes classically such that this thing happens? The answer is no, right? So this is why we are interested. Right, so this game was really played not by Alice, Bob, and this croupier, but by these 3 people here, and they actually got the Nobel Prize for it, for playing this game. All right, what was going on? So we have, okay, maybe in the interest of time, I let you think about it, in the break, or you can come to me and we can discuss. Like which kind of, what was the state here and in which direction was it measured? You can think about it by yourself. Are there any questions to this, or was this a is this too boring for you guys? All right. Okay, let's go to the real stuff. Let's discuss a bit entanglement in many body systems. And for this, we need some quantities which are sort of summarized here, and I would like to talk now a little bit about the quantities that we have here. So the situation I will have in mind in this lecture is a many body system that is in a pure state psi. And what we do is we cut out a subsystem, I call it A, and we look at entanglement between A and B. And how can we quantify this entanglement? So we have here a local Hilbert space, like radius of the particles is spanned by this state Sj. So the most general state that you can write down for this system, would be a sum over spins S1 to Sn. If this system consists of n particles, then you have coefficients S1, S2, Sn, and basis states S1, S2 up to Sn. Okay. And now we are interested in entanglement between A and B. So what I'm doing is I'm splitting these spins into a section A and a section B. Let's say A is formed by the spins S1 to Sj, and B is formed by the spins Sj plus 1 up to Sn. Without loss of generality, we split the spins into pieces. So this state can be written as you sum over S1 up to Sj. And Sj plus 1 up to Sn, and then you have this coefficient S1, S2 up to Sj, and Sj plus 1 up to Sn. And then you have here basis states S1 to Sj, for this system A, and then you have here Sj plus 1 up to Sn for the system B. So far I didn't do anything, I just rewrote this state. And now I'm getting a bit lazy. Actually, I don't want to write all the spin indices all the time. I just write this as sum over I from 1 to the Hilbert space dimension of A, and the sum over J from 1 to the Hilbert space dimension of E of Cij. I tensor J. I are states in A and J are states in B. Okay, so I just collected this S1 to Sj in index I and Sj plus 1 to Sn in an index J. So now we can ask, when are these things actually, when are A and B not entangled with each other? And they are not entangled if this Cij here can be written as Ui times Vj. If they can be written as Ui times Vj, then I can actually write this thing here as sum over I to the Hilbert space dimension of A, Ui Ia, tensor sum over I up to the Hilbert space dimension of B, Bi J, JB. So this is a state, let's call it a state phi that lives on A, and this is a state phi that lives on B. So if we can write this coefficient as a product, then the state factorizes, and then we definitely don't see any entanglement between A and B. And another way of thinking about this is that this coefficient, so you can think about this as a matrix. These are matrix elements of a matrix C. So this matrix C.
Question?
Yeah.
If you could switch to like black or blue, maybe.
Okay. So this matrix C, what it means is that it can be written as an outer product of two vectors. So you have a vector U times a vector V transpose, right? So this is a column vector times a row vector. Right? Row times column would be a scalar product. This is a matrix. And so you see that if there is no entanglement between A and B, our state loses a lot of its complexity, right? Because in general, for a general state, the Cij has dA times dB variables, right? In general, you have dA times dB variables in the state. But if it's not entangled, you have a vector with dA and one vector with dB, so the number of variables is just dA plus B. And this is sort of the idea behind tensor network methods and matrix product states, if you have heard about that. The the idea is to sort of decompose the coefficient vector of the state into these outer products, which contain much less information, and we can store them efficiently and do a lot of simulations. So this is, I mean, this is only if A and B are not entangled. But this thing can be generalized to the case when A and B are entangled with each other. So in this case, the coefficient, the most general case is that the coefficient matrix is actually a sum of such outer products. A sum alpha equals 1 to some number chi of numbers lambda alpha u alpha times B transpose alpha. So this is a sum over alpha, some numbers lambda alpha, column vectors alpha times row vectors alpha. And it turns out that any matrix can be written in such a form with positive values lambda alpha. So these lambda alphas, they are all larger or equal to 0. These vectors u alpha and b alpha, they are orthogonal among each other. So u alpha times u beta and b alpha times b beta is delta alpha beta. So they are orthonormal vectors. And this can be done for any matrix, such a decomposition. Any matrix that exists can be written as such a sum of products. And this is what's called the Schmidt decomposition or the singular value decomposition. So this is the singular value decomposition of the matrix. And if you plug this decomposition of this coefficient vector back in here, what you find is the Schmidt decomposition of the state that's written up here. Is this clear to everyone? If there are any questions, please let me know. Right. So, okay. So another thing is that we need is the reduced density matrix. The reduced density matrix you get by simply tracing out the subsystem B from the state, and then what you get, you can very easily see this from the Schmidt decomposition. So you get coefficients lambda alpha squared and projectors onto the states phi alpha. It's now what's sort of important now. It's now actually this lambda alphas that tell us something about entanglement. From the reduced density matrix, so from the reduced density matrix, rho A is sum over lambda alpha squared by A. So of course, all of you know that the trace of the density matrix must be 1. So this means that the sum over all this lambda alpha squared must be 1. And so we didn't have any entanglement. We just had one of these numbers, lambda alpha, which was 1, and all the others was 0. Then the state factorizes. So the amount of entanglement is somehow visible from the number and from the distributions of this lambda alpha. So what one does to quantify the entanglement is one defines this basically the Shannon entropy over these coefficients lambda alpha, over the coefficients lambda alpha squared. So this is just an entropy, and this means that the maximum entanglement actually we would have, if this lambda alpha is basically 1 is constant and is equal to 1 over the Hilbert space dimension of alpha, then you know that this means all these lambda alphas are equal, all the lambda alpha squares are equal, and this is usually what we call maximum entanglement. This von Neumann entropy you can also write as trace, just in terms of the density matrix. It's minus trace rho A log of rho. Right. So now you see sort of what the difficulty is if we want to measure such a von Neumann entropy in an experiment. The problem is that this thing here is a nonlinear function of the density matrix. Like for I would now sort of address the question like measuring entanglement in experiments. So problem is that everything we can measure in an experiment are sort of, you know, expectation values of some observables. Like in the subsystem A, we could measure the expectation value of some observable in rho A, which would be trace OA rho A. This is sort of extremely easily accessible in these experiments. But here we have a different kind of monster. You know, we sort of need the expectation value of the logarithm of this density matrix. And this is a priori not clear how do we get this. Now, something that people propose to do is quantum state tomography, which means is basically you measure everything which is possible. Actually, the Pauli strings, you know, Pauli strings are sort of, you know, all like tensor products of all combinations of Pauli matrices. And these Pauli strings, they form a complete basis for any operator. Like any matrix can be sort of expanded in the sum of Pauli strings. So you could write this reduced density matrix as a sum of all of these Pauli strings, expectation value of this Pauli string on the subsystem A times the corresponding Pauli string. So this means if you measure all possible Pauli strings, you could completely reconstruct this reduced density matrix, and then you have the reduced density matrix, and you could compute rho times log rho and trace over it. But this is something that's extremely difficult, right? Because we have an exponential number of these Pauli strings. For each side, we have 4, right? We have the identity x, y, or z. So we have 4 to the n possible things to measure. So this doesn't really work. So what are ways around? And what people started to do in experiments is instead of looking at this von Neumann entropy, they are looking at a simpler thing, which is kind of a proxy to von Neumann entropies, which are so-called draining entropies. The nth order Rayleigh entropy is defined as minus 1 over n minus 1, and then you have here the logarithm of the trace of the reduced density matrix to the nth power. So actually something I will talk about in the following is the second order Rayleigh entropy, which is just minus log of the trace of rho A squared. So this is still sort of difficult to measure because it's still, you know, it's still non-linear in the density matrix. But experimentalists developed tricks for addressing for sort of measuring the purity of the state, the trace rho a squared. And this is based on interfering two copies of the quantum state. So the idea for measuring the second order ring entropy, the idea for measuring the trace of rho a squared is to use the following formula. The formula that's written up there. So trace of rho a squared is actually equal to trace of the swap operator of rho a tensor rho. So what this means is if you double your system, you prepare the same state twice, and then in this doubled system you can measure sort of a linear observable. Then the problem comes linear, and it gives you rho a squared. The swap operator exchanges the two states on the two subsystems. So swap operator applied to phi psi, where phi is on I and psi on B, just exchanges the two states. So why is this the case? Has anybody an idea? Maybe you can try to prove this identity yourself, like the trace of the swap operator of rho tensor rho gives trace rho squared. What's extremely convenient for these kind of things are tensor network diagrams. You sort of what you do there is rho is a matrix, so you can represent it as something that has two legs, and the two legs correspond to the two indices of the matrix. So a product of two matrices in the tensor network language would be, you have a matrix A and a matrix B. These are both matrices that have two legs, and what you do, like the product would be you connect these two legs. Okay. And what would be the trace of A times B in this tensor network language? The language for the trace you sum over the outer indices. So this sort of would correspond to the trace. Now let's from this tensor network language you can immediately see that this is true. That so what we have now, let's try to draw is we have two copies of the state. So this is this is our first copy, this is our second copy. So this here is the tensor network representation of rho tensor rho. For instance, let's just play a little bit and let's compute the trace of rho tensor rho. So if you remember from your linear algebra lectures, the trace of the tensor product is the product of the traces, right? So this is trace of rho times trace of rho. And in this tensor network language, what this would correspond to is, like the trace connects these two indices and connects these two indices, right? So now you have the product of the two traces. But what happens if we insert a swap? You have this sort of picture. Maybe some of you can already see what happens if you have trace of swap in rho tensor rho. Like the swap operator exchanges the two indices. This here is the swap operator. Okay, the swap operator exchanges the two systems, and if you now trace over it, you get this kind of picture. And this is actually equivalent to this kind of thing. You can unwind this thing and you see that this is trace of rho squared. But you can also, this tensor network pictures, you can derive all of these identities very easily, but you can also try to do it with indices. This kind of many-body interference has been done in a lot of recent experiments. So how does this work in practice if you want to measure? So we want, what we want to have is the trace swap of row tensor row, no, or array tensor array. And you found your system, right? So you have this is your system 1, and this is your system 2. And the swap operator has this interesting or very kind of almost trivial feature that you can swap the two copies if you swap each pair. Right? So if you do a swap here and a swap here, so this is swap 1, swap 2, and you do a swap here, then this is the entire swap. You know, so the swap is the product, the tensor product over all individual swaps of pairs of qubits. So how do we measure such a thing? Like in an experiment, these things can always, so what you need to do in an experiment is you need to apply, to measure any observable. This is true for any observable. You need to apply a unitary transformation to the state that diagonalizes the observable. This is something that you always have to do. So expectation value of some observable, like trace of row times an observable. Of course, this observable can be diagonalized, right? So you have row, and this observable here is somehow some unitary transformation, a diagonal matrix that's diagonal in the measurement basis times u mega. And then sort of what you do is you use the cyclic property of the trace. So you need to apply this unitary transformation to your state that diagonalizes the observable, and then you can just, you know, sample and assign the diagonal elements of your observable. This is something that's always true. And the swap operator, does anybody know what the eigenstates of the swap operator is? Once these are the eigenvalues, and what are its eigenstates? These are the bell states, right? So you have, so there are these 4 bell states. You know, 5 plus is 1 over square root of 2, 0, 0 plus 1, 1. 5 minus is 1 over square root of 2, 0, 0, 0 minus 1, 1. And we have the state psi plus. So these 3 states are the triplet states, right? So 5 plus is 0, 1 plus 1, 0. And then there is the psi minus state, the singlet state, which is antisymmetric, and this one has a minus sign for the swap. So this is the eigenvalue decomposition of the swap operator. So what we need to do is to apply a unitary transformation here that transforms these pairs into the Bell basis. Maybe I can skip one slide. So actually, I worked it out for you. So this is kind of the unitary transformation that sends the states 0. So by this unitary transformation E here, so 0, 0 goes into 5 plus, and 0, 1 goes into 5 minus, and 1, 0 goes into psi plus, and 1, 1 goes into psi minus, or something like this. So this unitary transformation here sends these entangled Bell states into product states. So what we do is we apply this unitary transformation here for all pairs of particles, And then depending on which kind of configuration that we have here, could be a 0, 0, 0, 0, 1, 0, 0, 1, or 1, 1, we assign a plus or a minus sign to this, but only that 1, 1 gets a minus sign. Then we convert this whole sequence to a sequence of pluses and minuses, and we multiply all of them together. And then we repeat, like we average over this, and this gives us eventually the purity of the state. So the purity, what you do is basically, you do this Bell transformation, you count how often do you have a singlet here, and it's really this, it's the average minus 1 to the singlets. This gives us the purity of the state. Any questions here?
What's the process after? Why are you diagonalizing this?
So in these experiments, what you do is you make a snapshot of your state, right? And then you always see zeros and ones. That's the only thing that you can see, right? So in order, so in a way, the only that's my way of thinking about it. Like the only observable that you can measure is something that that is diagonal in these spaces, right? So like for any observable, so you need to basically transform to the eigenbasis of your observable and then measure. Okay. Right.
What was the bar?
This bar, it's just an average. This formula here basically means you do this transformation, and then you see like how often you get the singlet, right? So every time you have 1, 1 here, it means that you found a singlet, and if you found a singlet, you assign a -1 to this point, and then you multiply them together. So it's the average of a -1 to the number of singlets, because all other states receive a +1. Right. So I would like to make a comment about okay, maybe one more thing here before I delete this. There was an interesting thing that has been recently observed, actually, that so in this experiment, if we transform these bonds to this singlet, so we get and then measure, like our measurement outcome looks like this, right? So let's say we find here a phi plus, here we find a phi minus, here we find a psi minus, and so on, right? So like we found like from one shot in the experiment, we found one sequence of Bell states, and actually, what people discovered is you can, like this swap operator, you can actually decompose it into Paulis. Like if you compose the swap operator of 2 spins, like it looks like this, right? Here we have 0, 0, 1, 0, 0, 1, and 1, 1. Right, so the swap operator, these states here are unchanged by the swap, right? And these sort of are transformed into each other, right? This is how the matrix for a 2-qubit swap operator looks like. And you can compose this thing into Paulis, and in Paulis, this looks like this. Yeah, so it's the sum over all, xx plus yy plus cc plus identity gives you this matrix. So it turns out that these Bell states, these 4 Bell states, phi plus, phi minus, psi plus, and psi minus, These are eigenstates of the swap operator. You know, the swap operator has a -1 eigenvalue for this one and a +1 eigenvalue for the others. But these states are also eigenstates of these 4 operators here. Like these 4 operators, x, x, y, y, c, c, and identity, identity, they all commute with each other, right? So you know, x Pauli matrices, x and c, of course, do not commute. You know, commutator x and c gives 2iy, but these guys, they all commute with each other. So they have a common eigenbasis, and this eigenbasis is this bell basis. So there was a recent paper of from Robert 1. It's a science paper from 2022, I think, where actually they made the following extremely simple observation. If you have this measurement data, you can not only evaluate the swap on each for each of these bonds, but you can also evaluate expectation values of xx, yy, and cc here. But you can sort of, after you have this measurement data, you can select your favorite Pauli string, x, y, c, identity, c, c, x. You know, you just your favorite Pauli string, and then measure the tensor product of this Pauli in this from this measurement data. So you can measure trace of Pauli tensor Pauli in this state rho tensor. And this, remember what I told you before, the trace of the tensor product is the product of the traces. So this is like a trace of rho times Pauli squared. So what this means is you can, from this measurement data, select your favorite Pauli string and evaluate its square. This is the expectation value of the Pauli square. And you can do this for any Pauli you want, for all 4 to the n of them, that exist. It's pretty amazing. So it's really, if you do this kind of 2 copy measurement 1,000 times, let's say, then it's like you have measured each of the Paulis. There are 4 to the n of them, as if you would have measured all of them 1,000 times. No, not quite, you only get the square of it, so you don't get the sine of it. And with this argument, they constructed a quantum advantage argument. So the name of this paper is Quantum Advantage in Learning from Experiments. So what they show is if you have 2 copies of your state, you can do these bell measurements and can be exponentially faster for certain learning tasks. For instance, like here, learning the absolute value of a Pauli string. So this was just a very simple observation, which was made very recently, and which allowed one to construct the quantum advantage argument. Okay.
Just give you also the
slides. No, for the phenomenon entropy, you need the slides. Yeah. But the second order Rayleigh entropy is actually turns out like if you do the swap everywhere here and multiply together, it's actually the sum over all the Pauli squared. Right. So what these guys actually discovered is that, you know, trace of rho squared, the purity is the sum of all Pauli strings squared, sum of all Pauli strings squared. And what they discovered is you don't get not just this, but you can get each term individually, each Pauli string squared. Right, so it's 12. Hossein, can I still have 5 minutes to?
For us,
Okay, for us it's 10.
you can continue.
Okay. So I hope that that this was kind of interesting for you and you learned something. You learned something from this. For the remaining time, I would like to show some slides about some modern developments or some things I have been working on. Tal just asked about von Neumann entropy. So how can you measure von Neumann entropy? And there has been an interesting object that people started to study, which is the so-called entanglement Hamiltonian. I would like to talk about this a little bit. And this gives a route to at least not absolutely efficiently, but more efficiently measure von Neumann. So this is the entanglement Hamiltonian. And so the idea is basically you have this reduced density matrix, this reduced density matrix can be written as a Gibbs state, right? So if you have a reduced density matrix, you can write it as e to the minus theta h. You can always do that. This is just because the reduced density matrix is a positive semi-definite matrix. And this Hamiltonian here in the exponent, this is called the entanglement Hamiltonian. And now an interesting thing happens, like if your system has a local Hamiltonian, like let's say you have a Hamiltonian that is a sum of local terms. By local, I mean that this has just nearest neighbor and maybe next nearest neighbor interactions. Imagine you have such a Hamiltonian and you compute its ground state. Then at least for ground states of local Hamiltonian, it turns out that this entanglement Hamiltonian is extremely easy. Particularly, it has the same structure as your system Hamiltonian. It consists of the same terms. If your Hamiltonian has XX terms, this entanglement Hamiltonian will have XX terms. It has CC terms. It will have also CC terms. The difference is that there are some coefficients in front that are not here. And there will be some corrections to this, but for ground states at least, these corrections are extremely small. So this entanglement Hamiltonian is kind of the logarithm of the reduced density matrix, right? And you remember the von Neumann entropy was the expectation value of the logarithm of the reduced density matrix. So if you have this entanglement Hamiltonian, which you can just compute its expectation value and get the von Neumann entropy. All right, so let me briefly argue why this entanglement Hamiltonian is local. And then this then kind of connects to my second lecture, which is about Hamiltonian learning. So the point of this sort of outlook here is that if you're able to learn somehow this entanglement Hamiltonian, then you could potentially have access to its von Neumann entropy. Actually, you can see this from an argument which is called the eigenstate thermalization hypothesis, which works as follows. Imagine you have a local Hamiltonian and you diagonalize it, you get its complete spectrum. And you pick out some eigenstate somewhere from the middle of the spectrum. Then this eigenstate thermalization hypothesis is maybe something you have heard about in the past. What it tells you is that if you can compute some local observable in the state, this local observable looks like as an observable measured in a Gibbs state with an inverse temperature beta. And now actually you can argue, like in this paper, there is a derivation of this, that if this statement for this eigenstate thermalization hypothesis would be true for all observables in this subsystem A, it actually means that your reduced density matrix is just a Gibbs state, where this Hamiltonian in the exponent is the system Hamiltonian itself projected on the subsystem. So this is a very easy example where this entanglement Hamiltonian is very easy. Just the system Hamiltonian in itself, and it follows from eigenstate thermalization. It's not quite true because there are some corrections from the boundary of the subsystem, but this you can capture by having sort of not a global temperature, but a local inverse temperature. So you have a local temperature profile, and you can plot this temperature profile over the subsystem, and it looks like that. And the interesting thing is that if you make the subsystem larger and larger and larger, these profiles will change like that, but the height of the plateau is always the same in the subsystem. So in this Eichstätt normalization argument, there is nowhere it appears that this temperature profile should changes sort of with the size of the subsystem. And this actually leads to volume law scaling of entanglement entropy. So this is the reason, because the von Neumann entropy is the expectation value of this entanglement Hamiltonian. So it's the energy, basically, of this entanglement Hamiltonian, and energy is an extensive quantity, right? Energy grows with the volume of the subsystem. So this is actually where the volume law scaling of entanglement comes from. And then this has been known for quite a while, this Eichstätt normalization hypothesis argument that the entanglement Hamiltonian looks like this in highly excited states. And the question is now, I skip now some parts. How does it look in the ground state? In ground states, it turns out that these temperature profiles, they get deformed to parabolas. And it's actually kind of intuitive what this means. So remember that that the reduced density matrix was basically e to the minus sum over I beta I h I. So what's plotted here are these beta i's. So you can sort of think about them as a local inverse temperature. So what it means is that, you know, your subsystem has kind of a high temperature at the boundary. Here it's very hot, and in the interior it's cold. All that it means is the particles sitting here at the boundary to this subsystem, they have a lot of entanglement with the particles in A bar. So here the reduced density matrix is very mixed. We have a lot of non-zero of this lambda alpha squared eigenvalues. So why is this interesting? So this will be then the topic of my next lecture. It turns out that if you have, which will be about Hamiltonian learning in general, not about entanglement Hamiltonian learning. But it turns out that if you have a Gibbs state with a local Hamiltonian in the exponent, you can learn it efficiently. This was a very important result in quantum learning theory in 2021 from Anurag Anshu et al. At Harvard. So this means you can learn this sort of structure of the density matrix efficiently, and then, you know, compute for Neumann entropies or look at the entanglement spectrum. So what I will discuss in the second lecture is which kind of methods can we use to learn Hamiltonians, like from, if we have a state like this, how can we learn the Hamiltonian in practice? Once you have the Hamiltonian, you can use it for entanglement spectroscopy. In entanglement spectroscopy, what you basically do is you try to infer these eigenvalues, this lambda alpha squared eigenvalues, and they tell you something about topology in the state. And yeah, there are, as an outlook for this sort of presentation, there are some interesting future stuff I'm working on, like using quantum signal processing to infer entanglement Hamiltonians. And there are also generalizations to mixed states for which this lecture time is not enough. But I'm happy to discuss. I mean, we have a week together. You know, you can come to me all the time, and we can discuss. And I think I used up all of my time, so I'm going to stop here.
Thank you.
Other questions?
Sorry, I'm just a little unfamiliar with the term. What does like learning mean here specifically, actually?
Learning means is to basically find out what this Hamiltonian is just from measurements. You know, so the setup is always the same. So you apply a unitary transformation to the state, and you measure. You know, you take a snapshot and you collect a lot of snapshots of your state from different unitary transformations. And from this data, the question is, can we learn what the Hamiltonian is? Yeah.
You like on the one of the last slides, you mentioned like the entanglement growth volume, and then for like the ground state, it's just growth for larger volume. But then you assume that you have a 2D system. I think like for gap 1D systems, it actually grows just with the area law, not with the larger volume. Right?
That's right. Yeah, I was running a bit fast over this. So usually for gap 1D systems, you just have the area law, right? And for a critical state, basically, if you are at a critical point, then you have also an area law plus a logarithmic correction. So actually, in the slides here, I was assuming that this is at a critical point. Yeah. Yeah.
Between the two figures, the excited state and the ground state, what will be like?
A little bit louder.
What will be like the difference in the entropy, Renai entropy for the two states that you showed?
It's basically what he just asked, that in one case the entropy will scale with the volume of the subsystem, and in the other case it only scales basically with the size of the boundary. And the reason is that like if the temperature profile looks like this, like a parabola, then like your state is e to the minus beta h, like 1 over I beta I h I. These are your beta i's. So e to the minus something extremely large is very small, right? So here in the interior, this beta is super large. So here you don't get any contributions to your density matrix, but all the contributions comes from the boundary. While in this excited state, this temperature profile was sort of flat over the subsystem, and you get contributions from the entire one. Yeah.
Something I'm trying to incorporate with codes is the using a local filter Schmidt test between some decomposed state and an unsought circuit, same with this blackboard. Is there a way to get more information on like initializing the Hessian for updating the cost function to optimize variational parameters?
Or if you get more information about the Hessian, but this is a question. Yes. Yes, I think this is so. And it's kind of funny that you are asking this because I encountered this very recently. Maybe we talk in the break about this. Show you some examples about how incorporating the Hessian improves things in there.
Good. So I think we will take a 120-second break and we will come back. Okay.
I need a few more seconds.